This unit in the course is titled Laplace Transform. In this unit, I'll begin by introducing a representation technique for functions known as the Laplace transform. Then I'll present a number of properties of the Laplace transform, and I'll explain how the Laplace transform relates to linear time invariant systems. In addition, we'll consider several applications of the Laplace transform, including circuit analysis, stability analysis of feedback systems, and solving differential equations. Another important mathematical tool in the study of signals and systems is known as the Laplace transform. The Laplace transform can be viewed as a generalization of the classical Fourier transform. In other words, the version of the Fourier transform that does not deal with generalized functions, such as the delta function. Due to its more general nature, the Laplace transform has a number of advantages over the classical Fourier transform. First, the Laplace transform representation exists for some functions that do not have a Fourier transform representation. So some functions can be handled with the Laplace transform that cannot be handled with the Fourier transform. This allows the Laplace transform to be applied to a larger class of problems than the classical Fourier transform. Second, since the Laplace transform is a more general tool, it can sometimes provide additional insights beyond those facilitated by the Fourier transform. This makes the Laplace transform a more suitable choice than the Fourier transform for solving certain types of problems. When studying continuous time LTI systems earlier in the course, we saw that every complex exponential function is an eigenfunction of every LTI system. More specifically, we saw that for an LTI system script h, with impulse response little h, a relationship of this particular form here is satisfied. Recall from earlier that the function big H, appearing in this equation, is referred to as the system function. As it turns out, the formula here for big H, in other words this formula here, is nothing more than the definition of the Laplace transform of the function little h. So although we're only now being introduced to the Laplace transform, we've actually already used it unknowingly when we employed the system function to solve problems involving LTI systems earlier in the course. Since the Laplace transform has already been used to more efficiently solve problems involving LTI systems earlier in the course, this transform has already demonstrated its utility. Furthermore, as we'll see later, the Laplace transform has many additional uses beyond those seen earlier in the course.